Okay, it started. All right. Okay, so let's start. This is the second lecture of the mini course of Anton Petronian on Alexandrov spaces, CBB K spaces. Please, Anton.
Thank you. So today I'm going to spend some like the lecture talking about definition and something quite closely related to definition. And I plan to define CBB kappa space, but actually I will talk about CBB 0. So CBB is curvature bounded below by kappa. So this is slightly simplifies this case. Kappa 0 is slightly simpler. Instead of model plane, sphere, hyperbolic plane, or Euclidean plane, I simply take Euclidean plane. And most of the things straightforwardly generalize to kappa to general K. For positive case, sometimes you have you have to work a little bit more, but I will be happy to answer questions if you're interested in the general case. But there is no much difference, right? So first of all, I want to I need to discuss model angles and triangles, right? So if I have a metric space L and 3 points there, I can measure distances between the points. So I draw lines between them, but it's a general metric space, so there might be no lines, right? No geodesics between them. Then I can, after that, given these three distances, I can draw a plane triangle with the same distances. And in this plane triangle, say let it be x, y, z, that will be x twiddle, y twiddle, z twiddle. The more or less standard notation is that triangle x twiddle, y twiddle, z twiddle is a model triangle of xyz. Okay, if I need to emphasize that I want to work in the kappa plane, I should put kappa somewhere, right? But since in my case, I always assume kappa is 0, so I will omit it. So that's a triangle in the plane. And in triangle in the plane, I can measure angles. So for example, I can measure this angle, and this angle is simply denoted by comparison angle for x, y, z. So this little bit funny notation for the angle, I will explain later why I choose this notation instead of more standard one in Euclidean geometry, which would be y, x, z, right? But there is a reason to not to use it, right? Okay, so that's a definition, right? Whenever I have 3 points in the metric space, I can find this value, right? In principle, I could write a formula for this using cosine rule, but I don't want to, right? And so I have a function x, y, z. 3 points in the metric space is mapped to x, y, z, to the model angle or comparison angle. That's the same thing. Questions, comments? Okay, I hope that everybody knows it actually. Yeah, by the way, I think that the lecture is oriented to those who heard definitions of Alexandrov space but want to have like better understanding the interplay between the definitions. Okay, so now I'm ready to talk about a 4-point comparison. So now I have a metric space L. So L stays for lower Cauchy bound, but doesn't matter. And I choose 4 points in my metric space P, X, X, Y, and Z. And then I can measure comparison angle, model angles for. I can calculate 3 modulus angles with vertex P, PXY plus PYZ plus PZX. Okay, so that's the inequality. So L is a CBB 0 space if and only if this inequality holds for any points P, X, Y, Z in L. Questions, comments? That's I gave a definition of Cauchy bounded below.
So are we defining taking this metric space to be geodesic?
Sorry, your voice is breaking. So could you repeat it?
Are we taking these metric spaces to be geodesic?
No, I don't assume anything. I may take at the moment I may take any metric space and check this inequality for any 4 points. If it's inequality holds, I say that it's Cauchy bounded below by 0, right? But on the other hand, you're right that if like all applications comes from with additional, so when it comes to application, you additionally assume that L is a length space. And sometimes, like we don't pack it in our book, we don't pack it in the definition. So Cauchy bounded below is separate from length space, but most of the time people say that Alexandrov space is the CBB length space, right? So it's just inside, and usually it's complete, right? Completeness is so that's 2 assumptions which usually appear in the together with length spaces. Okay, yeah. Okay, so next thing is we will try to like, okay, we want to say, so eventually we want to work with geodesics in spaces with lower Cauchy bound, and we want to show that they exist, right? First of all, even if you assume that a space is length and complete and CBB 0, it doesn't imply that it's a geodesic space. So some points might be not connected by geodesic. All right, so let me give an example of such case. You may take S infinity in Hilbert space. All right, so that's infinite dimensional sphere. And it's, I didn't prove it, and I'm not planning to prove it, but it's rather easy to prove that this is example of space of Cauchy bounded below by 0, in fact by 1, right? But in the sphere you have plenty of geodesics that if you choose 2 opposite points, there are plenty of geodesics that connect them. I should say one more thing, that in metric geometry, when I say geodesic, it means always minimizing geodesic, right? It's not Riemannian term, it's a little bit different. Like if you use to term in Riemannian geometry, it's not the same. Okay, sometimes people say shortest path, sometimes minimizing geodesic, but yeah, Okay, so we have plenty of geodesic that connects to points. Now, assume I take, some orthonormal basis. So that will be element E0, and I have E1, E2, and so on. And now around every element of my basis, I cut little head from the sphere. Okay, that can be used, such head can be used to make a shortcut between opposite points, minus E0 and E0. And if I make it these small cuts bigger and bigger and bigger as n goes to infinity, but not approaching like some constant, but never like always strictly bigger than, strictly smaller than some constant epsilon. Then you get a space where there is no geodesic connecting opposite points. So whenever I choose some geodesic which is sufficiently close to the minimizing one, in the next head, I will get yet shorter one. Okay, so it will be no geodesics at all. Nevertheless, you have a property that spaces complete CBB 0 length spaces are G delta geodesic. What does it mean? That means that if I choose, I may choose everywhere dense G delta set in my for any so I have to define this thing, right? I have to define this. So that means that I may for any point P in my space, I may choose G delta dense set of points such that for any say for any point Q in A, there is a geodesic connecting P to Q. In fact, I may assume that it's unique. This geodesic is unique, right? So that's the statement, and that's theorem of Plaut. Plaut's. Let me just. So that's the Plaut's theorem, who, by the way, contributed quite a bit. Konrad Plaut, who contributed quite a bit to the theory of Alexandrov space without dimension condition of infinite dimensional spaces. Okay, so how to prove such thing? Assume I have like what? First of all, I want to show the following: that for there is a G delta dense set in L such that let's say set A such that for any point for any Q in A there is R such that the angle comparison angle, so P Q R, so this angle PR is nearly pi. So it's bigger than pi minus epsilon for any given epsilon. So why is it so, right? So if I choose a point, I may find a collection. So I may, so since my space is length space, I may find in a small neighborhood of points that almost lie on the geodesic. That means that this triangle inequality becomes almost equality. And once I see this angle must be nearly pi. So that, and it's true for some open sets here. So I could find open dense set such that this inequality holds for some r. So that will be my r, and q will be any point around here. And passing to intersection of all these sets, I will get G delta dense set. So it's like for large set of points, this inequality holds, like there is R such that this inequality holds for any positive epsilon. Now, it's easy to see once you have such point in this G delta set, it's easy to see that geodesic must be unique, right? If there is a two geodesics, so then you know that this angle is almost pi, and this angle is almost pi. And by comparison, this angle must be nearly zero. And then applying comparison, it's rather easy to, so what the definition of angle comparison, so what does it mean? That means that if I choose 2 points on the same distance from Q, then these 2 points must lie very close to each other. This distance must be very small. And this distance must be arbitrarily small, like once since this angle is almost zero. So that means that actually these two geodesics coincide. And applying pretty much the same argument, you can show that you can prove existence of geodesics. So what, in order to prove existence, what you have to show that there is a midpoint, right? Once you construct a midpoint between 2 points, you can iterate the construction and pass to the limit, right? And in the limit, you will get a geodesic. And to construct this midpoint, what you actually from the fact that your space is length space, you get almost midpoints for any epsilon. There is a point that lies almost in the middle. And the same argument shows that this sequence is Cauchy, and so it must converge, and from completeness you get midpoints. So questions, comments about this statement. So we get important like from now on we have plenty of geodesics in Alexandrov space, right? So like whenever we perturb one of the end of one of the elements of pair and can connect 2 points by unique geodesic. No questions?
I have a question here.
Yeah.
When you say G delta dense, is this just a set whose closure is G delta?
G delta dense. So G delta set is the intersection of countably many open sets. That's the definition of G delta set. And G delta dense set means that all your open sets are dense. So it's intersection of countably many sets such that each is dense. I'm not sure. Did I answer your question or not?
Yes, you did. That makes sense.
Yeah. Okay, so right, the standard definition, right? So like when you don't have measure, right, to say that most of points lie like have certain property, you have always in complete metric space you can always talk about G delta dense sets. That's roughly by Bayer theorem that tells you that most of points satisfy this property, right?
I have a follow-up question here. Could you just state the result again, Plaut's theorem?
Sure. Just a second. Here it is. So we have a complete CBB length space is G delta geodesic, and G delta geodesic means that for any point, like maybe I should write it nicely. maybe let me write it here. For any point P, there is G delta dense set A P in L such that for any Q in A P, there is unique geodesic PQ. Okay. So did I answer the question?
Yes. So is the idea that A sub P is almost the whole space?
Yeah, right. That's
Okay.
exactly right. So if you you remove little set in the sense in the sense of where categories, right? And for the remaining set you have unique geodesic.
Okay, great. Thank you.
Okay. Okay, so let me add one more. Okay, so now once I have geodesics, I could talk about angles. All right, so and angle comparison. That another equivalent way to define Alexandrov spaces, but which is good for people who has good background in Euclidean geometry, right? If you used to do Euclidean geometry, you may, I don't know, roughly you can do Alexandrov geometry the same way as Euclidean geometry, except some equalities supposed to be exchanged to inequalities, right? In a certain way, right? First of all, that like let me draw a picture. So I assume I have the following picture. I have 2 points X and Y in the space. I assume there is a geodesic between them, and I have a point Z on this geodesic. And yet I have another point P. So now I have picture P that like once I have such picture, it is described by 5 real numbers, right? Because I have one restriction. Z now lies between X and Y. Okay, so then one equivalent condition. So okay, so say L is complete. CBB 0 length space if and only if L is G delta geodesic plus for any picture like this, for any P, X, Y, Z as on the diagram, we have the following inequality. Z Px plus angle Z Py is less or equal pi. Right. So one way it's easy to prove, right? So since if I take the center Z and apply 4-point comparison, I know that model angles of these 3 angles add up to something smaller than 2 pi. But this angle, the last angle, ZXY, is exactly pi because it lies on the geodesic. right? By the way, the angle by definition lies between 0 and pi. It's easy easy to see from the definition. So you get this inequality, but in fact it's enough. Once you know that space is geodesic, G delta geodesic, this condition is sufficient to prove 4-point comparison, right? I will skip it. I will list some statements, some other angle comparisons, and after that we'll say what's the tool can be used to prove them, right? So I don't want to give all proofs. Okay. So questions about this definition? It's very close to the 4-point comparison which I described before, except that you made a restriction. Instead of talking about arbitrary quadrupole, you may talk about quadrupole with central point lying on geodesic between two others. But of course, you have to pay for this, and the thing you pay is this condition. You assume that your space is G delta geodesic. Okay, so next statement is okay. I will redraw the picture. X, Y, Z. And then I can write an equality between the comparison angles. X, Py must be less or equal than X, Pz. Okay, so at the point X, I can measure two comparison angles for triangle XZP and for triangle XYP. And for triangle XYP, the comparison angle cannot be larger. Oops, I forget the middle here. Okay, or you may equivalently you may describe it as the following way. You take a model triangle, X twiddle, Y twiddle, P twiddle, and take a point Z twiddle on the side that corresponds to Z. So this side is exactly the same as this one. Then this distance must be smaller than corresponding distances in the space, right? So that's second definition. And this definition, again, that's rather easy to prove equivalence of two statements. 4-point comparison, the previous comparison which I described, and again, of course you have to use that the space is G delta geodesic, right? But from this you get extra coloring, that you actually can define angles between geodesic coming from one point. So from once you have this statement, you know that if you move a point, say, assume I have point X, say PQ, right? And if I take some point Q bar on this side, P bar on this side, and whenever I move a point closer to X, the value, the comparison angle X, P bar, Q bar getting larger. So, and once I have this, I have a limit of this angle. So this angle must converge to something as P bar and Q bar converge to X. And this something is denoted by angle of the hinge, X, PQ. So this this notation of the hinge, this is simply shortcut notation for two geodesics, X, P and x cube, right? So from this second comparison, I get existence of the angles between any pair of geodesic, like existence of angle for any hinge, right? And this will be the third comparison statement, again equivalent to original one modular that the space is G delta geodesic. No questions? Okay. So finally, let me give one more definition. Yeah.
Yeah, I have. So
Yes, please.
suppose I know that my space has curvature bounded above by some k and bounded below by some k prime. So I can calculate a angle from above, right? Also, just like we do in cat kappa space. Will that angle be equal to this angle also?
Sorry, I don't know it. By the way, do you hear me? I mean, what about my voice? Do you hear me right? Because
I can hear you all right.
Yeah, but can you just repeat the question?
Yeah.
So
maybe slow because you're breaking up like I constantly.
Okay. So in cat K spaces, we can calculate an angle, right? Comparison angle by looking at the constant curvature kappa spaces and
Yes.
calculate that. And now here you are looking at the lower bound, right? Lower bound angle. So are those angles related somehow? That's what I'm asking.
Okay.
Will they be equal or something?
Let me say, I get only half of you, but my conjecture is what you're asking. Does the definition of angle depend on kappa? Is it correct or not?
Yeah, kind of. Yeah.
Okay, like I was afraid. Right. So no, it does not. Right. So if the triangle is very small, then kappa comparison x, y, z is nearly the same as kappa prime comparison angle x, y, z for small triangle. That's just simple calculations, right? So it doesn't really matter what kappa you use when you approach when 2 points approach the vertex of the angle. Is it? Are you sure that that was the question? Am I?
Yes.
Yeah.
Yes.
Okay. Okay. So can I continue or some other questions? No. Okay. So from now on, I can talk about angles. If I have a hinge, say x py, I can measure the angle between the of this hinge. And from the definition of angle, I also have that the comparison angle x py is always smaller, right? So that's we get it as a supremum of all comparison angles with so p x y with y bar and p bar sliding along the geodesic toward to x, right? So and in particular we get this inequality. So but and you could also right, so there is a equivalent way, but it's not enough, and that's like first thing, like funny thing about the definition. There is an open question, like whether this is equivalent, gives you equivalent definition. But what's sufficient to be, like, of course, it follows from the definition, but might be not equivalent. And what is needed here is that angle z, oh sorry, z p y plus angle z px is less or equal than pi. Whenever z lies between x and y. So right, so that's let me make a remark. Right, we are very close to defining Alexandrov spaces, and this is unknown whether this condition is really needed. Maybe this condition is equivalent to the original one, and it's not even known for surfaces. It's not even known for two-dimensional Alexandrov spaces. Right. So what's the tools? Well, how to prove these things? So there are two. Like the proofs are quite straightforward. So there are two things you have to use, right? One is this is the Alexandrov lemma, and another is a triangle inequality for angles. Okay. So Alexandrov lemma is, I think Sasha Lytchak already talked about this, but let me quickly say what it is. It's a lemma in Euclidean plane geometry, or like better say kappa plane geometry, right? It's some statement which holds for spheres, hyperbolic planes, and Euclidean plane. So imagine that you have a quadrilateral, you fix sides, and you think that at the vertices you have joints, right? So this quadrilateral can move. And when you move, you can measure different things. You can measure this distance. You can measure this angle, or you can measure sum of these two angles. Okay. And the statement is that these three quantities are monotonic with respect to each other. Each of these values completely determines the quadrilateral, and once it's fixed, the other are also fixed, and the dependence is monotonic, right? So that's one thing. And the other thing that is a triangle inequality for angles. If you have a space where angles are defined, right? So that means that whenever you choose, say, two geodesic coming from one point, you slide points toward the vertex, measure comparison angle, and you, no matter how fast they go, like maybe one go very fast and now another goes slow to the vertex, the limit will be always the same, right? That's the case for spaces with curvature, with lower curvature bound, right? Whenever you have a space with well-defined angles, the three angles, this one, and that one, satisfy triangle inequality. That's again very simple statement, very straightforward, right? So in these two statements, you combine them and the proof equivalent, and you can prove equivalence of the definitions. So that's, I finished the first part, right? And let me quickly say two more, maybe some questions. So yeah, right. So that's angle comparison are most useful for people coming with good background in Euclidean geometry. Now I will quickly say one statement about function comparison, and maybe, yeah, I will skip development. right? So another equivalent way to define Alexander space is the following. You take given a point P in the Alexander space, you can consider a function which is a distance function from point P squared over 2. And then f is one concave. You can write it as f double prime less than 1. And what does it mean? That means that if you restrict f to any geodesic, so gamma is unit speed, geodesic, then the function f composed with gamma, which is now real-to-real function, is so minus t square over 2 is concave, right? So that has perfect statement, right? That's a perfect statement about function, real-to-real function, right? And you can informally write it as f composed with gamma double prime less or equal 1, right? In distributional sense. And this is just defines this inequality, right? So there is a way to rewrite the Alexandrov comparison in terms of function, like a convexity of certain functions. So that's again very useful if you want to do, if you good at analysis, right? So that's okay. So I will skip development. Oh, by the way, maybe I should say here, right, that yeah, I will skip this part. So if no questions, I will come to I will talk about globalization.
Sorry, can I ask one question?
Yeah.
So the one concavity in there, is that specifically because you have CBB 0?
Right. If it's not 0, then formulas become more complicated, right? You have to apply certain modification of distance that depends on kappa. You take it composition with distance function to p, right? That's your function f, and the function f supposed to satisfy inequality like this, f double prime, right?
Okay, thank you.
So the formulas are just more complicated, but pretty much the same thing works, right?
And this is true if kappa is positive or negative?
Yeah, right,
okay.
right. You have to be careful, right? So if it's positive, then you have to, it works in the balls of radius pi. I mean, if kappa is 1, right? If kappa is 1, then this inequality holds in ball of radius pi, right? And doesn't work after, right? And there is a question whether you want to consider spaces like there is a disagreement, right? Say real line, does it have curvature greater or equal 1 or not? So, for example, in our book we think that's yes, and most of other people think that no, right? But it's like question, like a little bit, little weird part around definition. It's difference only in one-dimensional case. An upper-dimensional case, it doesn't matter. So, more questions?
Okay, thank you.
Yeah, I answered. Okay. So now the next thing is globalization. So what is it about? It's you may think that it's a generalization of Topanogov comparison theorem, and it says that local CBB 0 implies CBB 0. Of course, plus complete and length. So locally CBB 0 means that you check the condition, for example, the 4-point comparison in the little neighborhood of each point. If it holds, if for any point there is a neighborhood such that the comparison holds, then the space is locally CBB 0. And it turns out that in this case, it must be globally 0, globally CBB 0. So questions about statement? So this statement, so it's a generalization of Topanogov theorem. Topanogov theorem is in turns generalization of Alexandrov comparison theorem, which was in dimension 2, and Topanogov did it in arbitrary dimension. The proof does not change much, right? But it was an important observation that you can do the same thing in all dimensions, not necessarily 2, right? So after that, the proof of globalization theorem in most general case was done by in the original paper by Buraga, Gromov, and Perelman. And after that, but the proof was not very simple. And I will talk about some simplification which had a sequence of simplification which is done by originally the first statement was the first step was done by Konrad Plaut, and after that by Urs Lenk and Victor Schroeder, and the same proof just independently we did it in our book, right? So that's kind of, yeah. Okay, so what's the argument? So we want to use angle. We want to prove angle comparison, right? So we want to show that given angle, say it's equivalent way to say the following, right? So I assume I have a triangle PX PQ in my space. I measure this angle, and now I draw a comparison hinge with the same angle in the plane. Then this side must be greater than this side. Okay. So that's the comparison. And what do I know? So the second part with the angles is just easy to get from local statements. Right, and what I know that this inequality holds if the hinge I start is sufficiently small. So to measure the size of hinge, I can add up, say L. I can add up X, distance from X to P to distance from X to Q. So yeah, right. So let me just make I forget to make it an assumption. So I assume that L is compact, and in particular geodesic space. So there are 2 points connected by geodesic. But this assumption is not really serious, right? There are simple patches that generalize the proof which I will present to general L. Right. So in this case, I may say I can assume that this inequality holds for if L is smaller than some L0, and say strictly less than 0. And maybe it doesn't hold, like arguing by contradiction, I may assume that it doesn't hold for some hinge bigger than L0, right? So there is I can choose a little bit above L0, a little bit bigger hinge, such that this inequality doesn't hold anymore. And I want to, right, so I want to get a contradiction, to arrive to a contradiction, right? So what I can do, I start with my hinge, PQ, X, and I think of it as a first point in my sequence. So on each step, I choose the side of my hinge which is longer, and I go there by some distance, say 1/3 of this side, and I get new hinge. And next step, maybe it's still longer. I can choose this point, and then I travel back and forth. 3, maybe 4, and so on. X4, and so on. So I get a sequence of points and a sequence of hinges in my metric space. So by assumption that my comparison hold for smaller hinges. So for each hinge, say xi plus 1, and here might be p or q, depending who's on which side it was. The comparison hold. And I can use it. Okay, so now I will try to draw the comparison picture. Let me take this triangle and find a comparison triangle for this. P, x0, x1. Let me extend, so it's twiddles, right? Every time I use twiddle to denote a corresponding point in the comparison plane. Let me extend it and get a corresponding point Q twiddle. So first of all, by comparison, this angle is smaller than this angle, right? Smaller equal. So that means that this distance is smaller than comparison distance. So if I would draw the comparison hinge, the angle would be bigger, right? So once I have a big angle, the opposite side gets bigger, right? So that's that was my original distance, and after that it's getting shorter. Okay, now I know that comparison holds for this angle, right? Again, this angle is smaller than this one. And once I know this, I know that the complement angle here is bigger than the complement angle here, right? And that means that if I want to draw comparison hinge for this one, for x1, it will have small angle here, right? Say q twiddle double prime, and this distance will be yet smaller, right? So when I go from x1 to x0 to x1 and draw comparison hinge, the opposite sides getting smaller. And each time I pass from x1 to x2, from x2 to x3, and so on, it's getting smaller. So this this distance comparison side, opposite comparison side, can be is getting smaller. On the other hand, this angle is converging to pi. Why? Because if it's not, then on each step we would shorten the distance, the sum of sides considerably. right, by some positive delta. So we have just a finite amount of distance to, like, it still must be greater than distance from P to Q, right? It's, or better say it still should be positive, right? So in the limit, you get that this angle is pi. And in the limit, you get comparison. So if the angle is actually pi, you get comparison by simply by triangle inequality. So each time your opposite sides getting smaller, right? At the beginning, your opposite side is oh, sorry, something wrong, but right. So yeah, I messed up with something, but some signs of inequalities getting wrong in my head, but that's pretty much the proof, right? So we have monotonicity of sequence, and in the limit we get comparison. So on each step you getting picture worse and worse and worse and worse, and in the limit your picture is good, right? So that's a contradiction roughly. Sorry for this. I don't have much time to fix the statement, but I will show you the link to correct proof, right? Actually everything correct except I made some stupid change with sign somewhere. Right. I was planning to mention Kirsch-Brown theorem for the as another definition of Alexandrov comparison, but I don't have time, so better leave some time for the questions. Any questions?
Okay, questions, please.
No?
I have one. This might not really have a good answer, but is there a definition for Alexandrov space that you find yourself leaning on more often than the others?
So I like Euclidean geometry, right? And for me, angle comparison is the best, right? At least sometimes when I write a proof, it's easier to write using function comparison. But still, I think in terms of angle comparison. But it depends on your background, right? Like what you what you used to do, right? For some people, I know that function comparison is more useful, right? And in fact, sometimes proofs are very much shorter with function comparison. Yeah, did I answer?
Yeah, thank you.
Yeah. Okay, so finished. Yeah. So next time I will talk about convex functions and gradient flow. And in the last lecture, I will talk about finite dimensional Alexandrov spaces and some tools which appear, some extra tools which appear in the finite dimensional case.
Actually, can I ask a question?
Yes.
So in the previous talk, there was also a local to global theorem, but they required pi1 to be trivial. But
you mean in Sasha's talk, right?
Yes,
In,
yes.
Sasha Lytchak, right? Right. So
And
here you don't have it. You don't need it, right?
yes, so the proof there was similar, but somehow it's not needed here. Where is it?
It's not similar, right? It's just like, right? Yeah, I mean, in some sense, yes. You take triangles and so on. Like cat case is much simpler, right? The I know that it took a while to find this proof, right? And it took yet many years to make a proof like simple as you see. It's sufficiently simple proof after all. right? But it wasn't easy to find it. But the cat zero is rather straightforward thing, right? You just have thin triangles, and if you glue them together, the thinness propagates to bigger triangle, right? That's all, right? And here, observe that you don't break here. You don't break a triangle into like expected proof would be to break your triangle in some pieces, right? Use comparison locally and get a comparison for big triangle. And here it's not exactly like you need to apply it infinitely many times, right?
And why the expected thing is not working?
What? Why? What?
Why doesn't the expected thing not working?
This one, you mean?
Yes.
The infinite, well, it doesn't work. Just because it doesn't work, right? At least nobody able to do this infinite steps, right? You need to do infinite steps there. And in the limit you get it from triangle inequality.
But is there gluing in
No, it works like gluing doesn't work here, right?
Yes.
In cat zero case, triangles are thin, and you glue two triangles and you get thin triangles again. And in CBB case, triangles are fat. When you glue two fat triangles, you get nothing.
I see.
Right?
I see.
It's like at the very beginning of definitions, this development of cats and CBB are very similar, but actually they diverge. That's roughly the place where they diverge quite a bit. Yeah.
I see. Thank you.
You're very welcome. More questions?
Okay. If there are no questions, let's thank Anton. And I'll see you tomorrow. So the recordings are already available on the page for the lectures.